7 Earth-sized worlds around a tiny dim star, closer together than Mercury's orbit, locked in a perfect cosmic dance. If any hold air or oceans, nightside ice and eternal dayside storms would battle at the twilight ring. This is TRAPPIST-1, 39 light-years away. In minutes, the fastest tour of everything we know, and what we still don't. The story began on the ground, with the TRAPPIST telescope in Chile, which first spotted hints of planets in 2016. Then, NASA's Spitzer Space Telescope stared at the star for over 500 hours, confirming the initial worlds and discovering more. The system was unveiled in 2017. Its star, a dim, cool ember, is perfect for catching the slightest flicker when planets cross its face. Close by in cosmic terms, yet far enough that every detail takes immense patience. 7 worlds, labeled B through H. All are roughly Earth-sized, ranging from about 3/4 to just over 1¼ times our planet's diameter. Their years are breathtakingly brief, from 1½ days for the innermost planet to nearly 19 days for the outermost. This entire solar system is a compact clockwork, packed so tightly that all 7 orbits would fit comfortably inside the path of Mercury. Let's meet them, one by one. Planet B, the fastest, is likely a hot, barren rock. Planet C is similar, with a slightly lower density. Planet D is the lightest of the 7, possibly with a large ocean or a thick, steamy atmosphere. Planet E is the densest, almost certainly a rocky world. Planet F is thought to be a water-rich world, perhaps covered in a global ocean. Planet G is the largest, also potentially holding significant water. And finally, Planet H, the coldest and most distant, is likely an icy body. They move in a near-perfect resonance chain, a delicate gravitational choreography. For every 2 orbits of the outermost planet, H, the next one in, G, completes 3. For every 3 orbits of G, F completes 4. The pattern continues inward with ratios like 4:6 and 6:9. This intricate dance not only keeps the system stable, but it also allows astronomers to measure the tiny gravitational tugs between the planets, letting us weigh them with exquisite precision. Within this tightly wound web lies a temperate band, the habitable zone. For TRAPPIST-1, this zone is incredibly close to the star, encompassing the orbits of planets E, F, and G. Habitable is a carefully chosen word. It simply means that surface temperatures could, theoretically, allow liquid water to exist, but only if the right kind of atmosphere is there to support it. Being so close to their star, these worlds are almost certainly tidally locked. One side is trapped in endless day, facing the dim red sun, while the other is frozen in perpetual night. Life as we know it might struggle on these extremes, but along the twilight ring, the terminator, a sliver of permanent dawn or dusk, could offer milder conditions, especially if a substantial atmosphere can circulate heat from the day side to the night side. So, what are they made of? The transit timing variations, those tiny gravitational tugs between planets, reveal their masses. When combined with their sizes, we get their densities. The current data indicates that all 7 are primarily rocky. Their densities are slightly lower than Earth's, suggesting they are not simple iron rock balls, but may contain a significant fraction of lighter materials, or volatiles, like water. Some could hold modest water fractions, perhaps up to 5% of their mass. This could be locked away as ice, held as vapor in an atmosphere, or pooled in vast subsurface reservoirs. But the evidence does not favor universal ocean worlds. The densities are too varied. Each planet likely tells a different story of its formation and evolution. The star itself is small and cool, yet fiercely active. Red dwarfs are notorious for their violent flares, which can erupt without warning, bathing the close-in planets in a torrent of high-energy X-rays and charged particles. For any potential atmosphere and for life on the surface, that's a profound challenge. Over billions of years, repeated powerful flares could strip away lighter gases like hydrogen and helium, or even erode denser atmospheres. Whether a thicker, heavier atmosphere can survive depends on a delicate balance: the planet's own magnetic field, its initial composition, and any geological activity that might replenish gases from the interior. We are actively testing those possibilities now. How do we learn all this from so far away? The primary tool is the transit method. We watch for the tiny periodic dips in starlight that occur when a planet passes in front of its star. The depth of that dip tells us the planet's size. The timing of each dip maps its orbit, and by stacking these observations together, we can see the subtle ways the planets pull on each other, revealing their masses, their interactions, and more. TRAPPIST-1 is an ideal target for this technique. Its planets transit frequently, giving us many opportunities to observe them. And because the star is so small and dim, the dip in light caused by an Earth-sized planet is much more pronounced than it would be for a sun-like star. Even faint whispers of information stand out clearly against the quiet backdrop of this tiny ember. The story so far has been a collaboration across generations of telescopes. The TRAPPIST ground-based telescopes began it. Spitzer stared for weeks on end, extending the light curves and discovering the full family. The Hubble Space Telescope scanned for signs of puffy, hydrogen-rich atmospheres and found none. Each instrument added a precise, crucial thread to the tapestry. And now, JWST. Its powerful infrared vision is our sharpest tool yet for sniffing out atmospheres. Early results have confirmed Hubble's findings. There are no thick hydrogen-helium envelopes for the inner planets. For planets B and C, we're now placing tight limits on whether they have any atmosphere at all, particularly one rich in carbon dioxide. A null detection is not a failure. It is a critical piece of the puzzle, telling us what these worlds are not. The temperate trio, E, F, and G, remain the biggest question. Do they hold thin, Earth-like atmospheres, thicker, Venus-like ones, or are they too nearly airless rocks? Current evidence is cautious, and the data is still being gathered. We simply don't yet know. The silence from the cosmos is not an answer, but an invitation to listen more closely. If atmospheres do exist, climate models sketch out fascinating possibilities. Strong winds could carry warmth from the permanent day side to the night side, preventing the atmosphere from freezing out. Thick clouds could form along the terminator, or perhaps a giant eyeball cloud pattern would stare perpetually at the star. The worlds could be stark and barren, or surprisingly gentle. Magnetism matters immensely. A global magnetic field, generated by a molten, rotating core, can act as a shield, deflecting the star's harmful winds and protecting an atmosphere from being stripped away. But these magnetic hearts are impossible to see directly from light years away. For the TRAPPIST-1 planets, this remains one of the great open mysteries, a key variable in their potential for habitability. How did this perfect clockwork form? The leading theory is that the planets formed farther out from the star, where water ice and other volatiles were more plentiful. Then, they slowly migrated inward, drawn by gravitational forces, and were captured one by one into the stable resonance chain we see today. TRAPPIST-1 is a pristine laboratory for testing these theories of planetary formation. Nearby, small and rich with signals, TRAPPIST-1 is our benchmark system for studying rocky exoplanets. It is the Rosetta Stone for Earth-sized worlds around other stars. Each transit we observe refines the picture. Each new spectrum, each null detection, narrows the vast field of possibilities. The path forward is clear: more observation, more JWST time, staring during eclipses and transits to build up a clearer signal. In the coming decade, future giants, the extremely large telescopes on the ground, will join the search, perhaps able to directly detect atmospheric oxygen. And dedicated missions like Ariel will map the atmospheres of hundreds of exoplanets at scale. Patience and repeated careful looks will reveal what endures. Take a slow breath in and imagine standing on one of these worlds. Imagine 7 skies, each under the same small red sun. And a long, slow breath out, releasing all the questions, all the possibilities into the quiet, patient dark. We don't have all the answers. Not yet. The story of TRAPPIST-1 is still being written, one photon at a time. But with careful light, steady timing, and time itself, this remarkable system will speak.